external failure, which would be the costs associated with problems found by customers and users after release. And obviously, non-conformance costs and internal costs include fixing the bugs and retesting. For external costs, it not only includes fixing bugs and retesting, but also things like less tangible things like dealing with angry customers, dealing with damage to the company image, dealing with lost business, and so forth. So testing is a way to reduce the overall cost of quality. And I'm going to show you a hypothetical case study of that. I'll show you a real case study a little bit later in this presentation, but we'll start with a hypothetical to illustrate the point. So for conformance costs, we're just going to look at testing. We're going to look at manual testing, automated testing, and static testing in the form of reviews. We're going to omit prevention costs of quality assurance, because we're trying to analyze the value of testing, so we want to stay focused on a single variable here. For non-conformance costs, we're going to look just at internal and external failure. We're not going to look at any intangibles that might apply, which essentially means that we're really underestimating the value in some ways. So we're not trying to count customer goodwill and damage there too as part of our calculation. Now, in this hypothetical case study, we're going to assume that we've got 1,000 must-fix bugs in each quarterly release. So we're going to release software every 3 months, and there are 1,000 must-fix bugs in that have to be found and fixed at some point, either prior to release or after release. Sorry, we had a particularly big gust here. It was a little distracting. Now, we're also going to assume some bug fix costs, hypothetical bug fix costs, $1 to fix a bug found in reviews, $10 to fix a bug found in program or unit testing, $100 to fix a bug found in testing by in a formal test group, and $1,000 to fix a bug found by the customer. Now, these are hypotheticals, and they will not hold true in your organization, but what will almost certainly hold true in your organization is the multiplicative increase from one phase to the next. That definitely is something that we see quite a bit. Okay, so let's start with the baseline scenario. If you want to calculate a return on investment, it's always in comparison to something. And so, in comparison to what? Well, the baseline is there's no formal testing. All right, so we're not doing any formal testing at all. So there are 1,000 bugs in the product, and let's assume that the developers in their unit testing find 250 bugs. This, by the way, is pretty typical. Unit testing has an average defect removal effectiveness of 25%, according to Capers-Jones. So this is a fairly average type of number. So 250 bugs are found, leaving 750 to go out to the customers. And we see the calculation of cost of quality over there. We've got our cost of conformance, which just includes the cost of testing. We're not spending anything on formal testing, so there's no cost there. We have cost of internal failure, which includes the cost of bugs found in development and test, which is just the bugs found in development at this point because there's no formal testing. And then we have the external failure, which is the cost of the bugs found fixed the customer side. It's $750,000. So our non-conformance costs are a little over $750,000, and we're definitely not dealing with happy customers here. I mean, one of the things that's sometimes confusing about cost of quality is it would sort of seem like, well, the higher the total cost of quality, the more we're investing in quality and the better things are. Actually, usually it's the correlation is the opposite, that the lower cost of quality is associated with a higher level of quality in the field because of the escalating cost. And so for $750,000 in cost of quality, we're buying some very unhappy customers. So let's suppose we put a formal manual testing operation in place with an independent test team. So we see the math here. We are investing $70,000 per quarter in costs of detection. So this is the cost associated with just creating tests, and running tests once. It doesn't include things like regression testing and other sorts of repeated testing that has to happen after bugs are fixed. So let's assume that the testers now, the developers continue to do their unit testing, still finding 250 bugs, and that's really important. We want to make sure that the product is going to the testers in a relatively mature fashion. So the 750 bugs come to the testers, and they find about half of them. They find 350 bugs. That's a 50% roughly defect detection effectiveness, which is pretty low, but it'll get better over time, as you'll see. Now, what happens then? So 350 plus 250 is 600. So now that leaves only 400 bugs to go out to the customers. And I say 400, that's still pretty bad. Yeah, but it's a lot better than 750, which is what it was before. So if you look at this column here, it says manual testing, you can see that our cost of conformance, which is our investment in testing, is $70,000. That's up, but our cost of non-conformance is way down to $440,000 roughly. Our overall cost of quality now, being the cost of conformance plus non-conformance, is about $500,000 on a $70,000 investment. So this $250,000 reduction in the cost of quality for that $70,000. So that's the net benefit. And so our return on investment is 350%. So that's pretty good. Nobody's getting 350% in the stock market these days. But that actually is not a typical number. We typically see a number higher than that, as I'll get to a little bit later. And certainly the customers are happy, right? So we're spending $250,000 less on bugs, but we've got happier customers. So that's an illustration of what I was saying a moment ago, that cost of quality goes down and quality goes up. Now, suppose that we introduce automation. So suppose we invest $150,000 in getting some tools set up. Now, this could be tool licenses, or it could include, we go get something like Selenium and do open source and hire some people to come in and work on building the infrastructure and so forth. So that could be the $150,000. Now the trick here is that you have to amortize this investment, this upfront investment in building these testing frameworks over some period of time. And a fairly typical amortization period is 3 years. So that'd be 12 quarterly releases. So you can see that we've got a $12,500 cost associated with the automated testing column over here. Let me just highlight that so you can see that. That's this column here, and then you see the $12,500. So our total investment is now up to $82,500. And let's suppose that allows us to find about 40% more bugs, which is not an unusual number. You do better regression testing and reliability testing and performance testing and so forth using automated tools of various kinds. So let's suppose that we get now 500 of the 750 bugs delivered to us. So that's where our defect detection effectiveness is now 66%. We're finding 2/3 of the bugs that are delivered to us in testing. And you can see what happens now. So 750 bugs removed by the developers and the testers together, leaving only 250 bugs out to the customers, which is 1/3 of what it was in the first place. So the customers are obviously going to be much happier.